Okay, we move to the next thing, the net energy release, which can be calculated from the mass balance, turned out to be 26.7 mega electron volt. If the sun were to continue to radiate at the present rate, about 130,000 kilowatt hour, it would take about 75 billion years to exhaust its supply of proton. Okay, in order to consume all proton completely, it would take 75 billion years. So it's 75. รับผมเข้า YouTube โอเคผมก็รอใช้สิทธิ์อยู่นะครับโอเคไม่ค่อยได้เข้าแวะดูนะครับ Alright, I hope that everyone has no problem. Okay, the next thing for two nuclei to fuse. No. The fundamental challenge of nuclear fusion is that they requires nuclei. They require kinetic energy for the nuclei to overcome the repulsive Coulomb force between them at a close distance. For two nuclei to fuse, they must come together within the range of nuclear force, typically on the order of 2 femtometer. At the distance of 2 femtometer, the potential energy of two protons is on the order of 1.1 10 to negative 13 joule, or 0.7 mega electron volts. That's the energy we need to supply to the nuclei. Okay. Yes. Next one. The temperature T for a gas with the average translational kinetic energy. This is from the Boltzmann constant, right? From the typical gas calculation, in order to get that amount of energy in the SI scale, the temperature, this is the Boltzmann constant, 1.38, 10 to negative 23, and the unit for that. You need to have the energy T on the order of 5,000 million Kelvin, okay, so that you could supply the kinetic energy to the nuclei at this distance. The temperature must be on the order of millions of Kelvin, so the nuclei can have enough kinetic energy to overcome the electric repulsion, and it can achieve fusion. So the nuclear fusion could not take place on Earth. It's very difficult to take place. So right now we could not build up the chamber or the experimental site for the nuclear fusion on Earth, because it requires extremely high energy, million Kelvin. Okay. Fusion reaction that appear most promising for human is the deuterium-2 because we could find deuterium from the sea, and tritium. Tritium is even the heavier isotope of the hydrogen. Reaction sequence is the following. You start from deuterium-2, two particles of the deuterium-2. You get the light version of helium-32, and you get neutron. Okay, and once you want to find the liberated energy or the releasing energy, you could find a mass difference, and you multiply it with 931. ผมต้องปล่อยคุณเท่าไหร่นะ950ใช่ไหมครับ and you will get you substitute the mass of the deuteron 2 times because we start from 2 particles of deuteron. The next thing is we subtracted by the mass of helium-32, the light version of helium, and here is the mass of the neutron, right? In atomic mass unit, if you multiply with 931, you get the liberated energy of 3.27 or 2677 mega electron volts. And the next sequence of this process is that, or the next possible way is that you start from 2 particles of deuterium-2 and you get tritium and proton. Okay, that's also a possible case. And in this way, you will find that the mass difference could be also computed, and the released energy will be 4.0315. It's even bigger than the helium-32 version. Let's talk about the released energy in the reaction of helium-32 with deuterium. If you start from helium-32 and deuterium-2 and if the result turns out to be helium-42 and nucleus of hydrogen 1 or the proton, what is the release energy then in this case? And of course, we use a typical way in order to find the released energy, and that way is the mass difference, right? The mass difference. So we start from 2 particles here. So we substitute the mass of helium-32, the light isotope of helium, and the heavier isotope of hydrogen, which is deuterium-2, mass of deuterium, and we subtracted by the mass of the output, which is helium-42, and the mass of the proton or mass of hydrogen 1. And it turns out that the released energy is becomes 18.352 mega electron volt, which is quite high. Okay, if we can really build up this nuclear fusion. Okay, what we can do is only the calculation from theory, how much energy we could get, right? And you could see that the released energy is quite high, but from the uranium-235, you get somehow 200 mega electron volt, right? But this one is 18.352 mega electron volt. All particles in nature are subject to 4 fundamental. Now we finished the nuclear fusion, and we will move to particle physics as same as M605. All particles in nature are subject to 4 fundamental. Before we go to particle physics, we will talk about 4 fundamental forces, because the forces could be explained by the meditation or the exchange of some particles. Okay, so it has some relation to the particles in physics. Okay, so if we make a conclusion, you could see that every force in physics could be classified into these 4 types, which are strong force, electromagnetic force, weak force. This force may not so widespread or may not easily heard before, right? Weak force and gravitational force. Of course, you may have already seen gravitational force, which is the G, right? The G, which is the gravitational acceleration on Earth, and if you multiply it by mass of anything, you get the force, right? Okay, let's move to the next thing. Here are 4 fundamental forces, and each force could be explained by particles. Okay, let's see the details of each force. Okay, let's start from the strong force. Strong force is the greatest force in all these 4 categories. Strong force is responsible for the tight binding of quarks, okay, to form the neutrons, okay, to form the protons. It's also responsible for nuclei. Okay, if you want to let neutron and proton to stay together, and that's the task for the nuclear force. Nuclear force is a member of the strong force. Okay, and the strong force represents the glue, okay, that holds the nucleon to stay together, and it is the strongest of all 4 fundamental forces. The strong force is a very short-range force. If we are far away than 1 femtometer, or on the scale of femtometer, the strong force will not exist. Okay, it exists only in the scale of femtometer, 10⁻⁻⁵ meter. Let's talk about the electromagnetic wave that we have seen in the last semester, that has E field and M field, which is magnetic field. Magnetic force is about 1 by 100 times. Okay, it's less stronger, it's 100 weaker than the strong force. Okay, and it is responsible for the binding of atoms and molecules. Okay, if you want to join 2 atoms together, okay, they're gonna have the covalent bond and so on. They have to share electron. Okay, and yeah, that's the bigger scale than the strong force inside the nuclei. The electromagnetic force is the long-range force. Okay, if you transmit the electromagnetic wave for several kilometers, you still get the signal, right? For example, the signal in your mobile phone, the signal for your television is transmitted from the station, which is quite far away from us. So the electromagnetic force is a long-range force that decreases in strength as the inverse square. So if we are far away from the source, we will get weaker energy or the signal of the electromagnetic source, right? And the weak force, right, is the third one, is a short-range force. It's a short-range nuclear force that it exhibits in the instability of certain nuclei. The weak force is involved in the mechanism of beta decay. Its strength is 1 million weaker than the strong force. Let's talk about the 4th force, which is the gravitational force. The gravitational force is a long-range force. You could get the gravitational force from the sun, but it's not strong. Okay, the strength of the gravitational force is about 10⁻⁻43 times that of the strong force. Is very, very weak here. Although this familiar interaction is the force that holds the planets, star, and galaxy. Okay, the planet, the star, the galaxy stay together by due to the gravitational force. Its effects on elementary particle is negligible, so we would neglect the strong force. The gravitational force to the elementary particles. The gravitational force is by far the weakest force of all 4 fundamental forces. And modern physics often describe the force between particles in terms of interaction, in terms of action of few particles, or it's easily known as quanta, which is the plural form of quantum. Forces between two particles are conveyed by the exchange of few quanta. This process is similar to the covalent bond between two atoms created by an exchange or sharing atoms. Okay, so when you exchange the particles, so you have the force to each other. That's the meaning of this sentence. And in chemistry, in the bigger scale, they have the covalent bond, right? And that in that bond, the atom just share the electron, right? So we arrive at the summarization, or summary of 4 fundamental forces. There are 4 forces, right? Gravitational force, electromagnetic force, weak force, and strong force, right? Relative force, right? If we say strong force is the greatest amount, so we would say that this is this has value of 1, right? So it's unified. It's scaled to be number 1. So the other, which is weaker, should be less than 1. For example, gravitational force, it is around 10 to negative 43 to 10 to negative 38. Okay, and electromagnetic force is 100 weaker than the strong force. The weak force is not so much weaker. It's weaker than electromagnetic force. It's around 1 million or 1 million, 10 million weaker than the strong force. The range of these four forces will take place. The gravitational force will have the range of infinity, and the force decreases with the distance square. Electromagnetic force too. We can get electromagnetic forces in infinite distance, and the strength will decrease with the distance square. Okay, the weak force is given by 10 to negative 18. Okay, this is the distance in meter, so it's even less than 1 femtometer. It's 1 by 1,000 femtometer. It's very, very short. And for the strong force, we are on the order of 1 femtometer, okay, or less than that. The type of the force, whether it's repulsive or attractive. Gravitational force is attractive, right? Because if you jump onto the air, okay, the earth will bring you back to the ground, right? And that's the attractive force. Electromagnetic force could be either repulsive or attractive force. And the weak force can be also either repulsive or attractive force. The strong force can be either repulsive or attractive force. Okay, both. And carrier particle. What is the carrier particle of gravitational force? It is expected to be graviton. Okay, graviton is not yet discovered. Okay, electromagnetic force. What is the particle that carries this force? It is photon. Okay, photon doesn't include only the light, but also any frequency of electromagnetic wave. And weak force, what is that? What is the carrier particle? The carrier particle of weak force is the carrier particles of the weak force are W plus boson, W minus boson, or Z0 boson. And what about the carrier particles for the strong force? It's expected to be gluon, okay, from the word glue, okay. So what is the status right now, how human has discovered the carrier particle? The carrier particles for the gravitational force is graviton, but graviton is conjectured, okay, it's not yet found in experiment, but it is predicted to exist. What about photon? Photon is already found in experiment. What about weak force? What about W plus boson, W minus boson, or SCI33206 boson? Well, all these three particles have already found in experiment. What about the gluon, which is the carrier particle for the strong force? Gluon is not yet found for human. Gluon is not yet found by human. It is expected to exist. Okay, so it's conjectured. Yeah, that's the status right now. Maybe in your generation, maybe I have passed it away. All these two things may have been found in laboratory or in experiments already. Okay, it could take place. Let's talk about quarks and other particles. Quarks, leptons, and the particles that convey forces. What is lepton? Lepton, for example, the electron. Okay, electron is an example of lepton. The particle that convey force, for example, photon, are now thought to be the truly fundamental particles. Before we go to the full table of elementary particles, let's talk about direct theory. For every particle, there is an antiparticle, right? As you know, electron has its antiparticle, which is positron, right? And the antiparticle would have the same mass as that particle, but in the opposite charge. Not only the opposite charge, but also opposite number of something. An antiparticle is usually designated by a bar over the symbol. For the particle, for example, except for the positron. Positron doesn't have bar above. We just replace the negative here on electron to be plus. Okay. It depends on the people who want to write down. Among the exceptions are the photon and neutron pion, denoted by pi 0, which are their own antiparticles. They don't have antiparticles, they are already their own antiparticles. Okay, photon and neutron pion. You will see pion later. When a particle meets its antiparticle, both particles will be annihilated. And the annihilation will give you high energy photons or gamma, right? It is useful to classify particles in terms of their interaction. We will distinguish also between boson and fermion, right? Boson always have zero or integer spin, while fermions have half integer spin, right? 1/2 or 3/2. That's the fermions. Fermions obey the exclusion principle, and boson do not. What does that mean? It means fermions could not take place or stay at the same location and at the same time. But if you talk about that in terms of quantum theory, the fermion cannot have the same quantum number, same quantum state at the same time. So they cannot stay at any location together at the same time. That's the Pauli exclusion principle. But boson could stay together, but boson will follow the property or property theory by Boson. Okay, we arrive at the standard model of elementary particle. Here we have fermion on the left, right? Fermion is right here, and boson is right here on the right. Okay. So what happened? And as you see, here is the typical particles, right? On these three columns, and these three columns, you get antiparticles, right? For example, the up quark. Let me introduce again. Here is fermion, and here are bosons, right? The fermion could be classified into two categories. The first one is quarks, and the second one is leptons. Quarks will be the one that's related to a strong interaction, but this one will be related to the weak interaction. Okay, let's talk about quarks. The smallest one for the quark is the up quark and down quark. The mass of the up quark is 2.2 mega electron volt per c square, and the charge will be half integer, right? The charge will be 2/3 of electron charge, and down quark is more massive, is 4.7, and charge is negative. Okay, and the spin number is 1/1/2. That's the half integer spin number for the fermion. But the gluon could have spin number as number 1 or 0. That's different. Okay, the up quark, the up quark had its own antiparticle, which is known as anti-up. The anti-up has the same mass as the up quark, but the charge is different. 2/3. This one is negative 2/3. Okay, and now we go to the bigger version of quark, which is sharp quark, and sharp quark and straight quark. Okay, it's on the order of 1.28 giga electron volt per c square, and this one is 96 mega electron volt per c square. Both will have their own antiparticles with the same mass, but the charge will be opposite, right? If this one is positive, the antiparticle will be negative. If this one is negative, the antiparticle will be positive. Okay, with the same mass and spin number. So let's talk about the bigger quark, and they are top quark and bottom quark. You could see the mass here is 4.18, and 137 is very, very big. And the top quark and the bottom quark have their own antiparticles with the same mass and the opposite charge value, the same spin numbers, 1/2, right? The big quark are not so stable. Okay, they're gonna decay to the smaller quarks. And let's talk about leptons. The one that is very well known to us is electron, right? Electron has a mass of 0.511 mega electron volt per c square. But of course, the charge for electron is -1 because its electron is negative, and we use the charge of electron to be the reference, right? So yeah, it's -1. Spin number for electron is 1/2. Okay, and that's a negative one. The bigger version of electron is muon. Okay, muon is actually the bigger electron. It has the mass of 105. Okay, 200 times 200 more massive than the electron. But muon will not be so stable. They're gonna it's gonna decay to electron later. But the people have discovered this bigger particle because they use the particle accelerator. You know particle accelerator, right? ทุกคนรู้จักเครื่องเร่งอนุภาคใช่ไหมทุกคนรู้จักเครื่องเร่งอนุภาคไหม particle accelerator เป็น if you wanna but it's not difficult to predict it. There might be bigger quarks or leptons if you have the bigger or better particle accelerator. And the place you can study something or discover something about elementary particles is in SAT. Oh no. It's in sand. Okay, I may not say it properly. It's in CERN. You can say it's CERN, right? In English, CERN. CERN came from the French word, right? Council European Polar Researcher Nuclei. Okay, this is French. I don't know how to pronounce it in French, but yeah, this thing. Okay, I would not pronounce it correctly. I have never studied French. Okay, and if you want to discover new or bigger particle, you should go to SAN or to CERN. Okay, if you translate it in English, it's going to be European Council for Nuclear Research. Okay, and there the people are studying something about elementary particles like quark, leptons, and so on. If you want to see the image of sand is somehow like this. Okay, you just do the PhD. If you fall in love with particle physics, you just do the PhD and try to be very, very good, okay, and apply for a job in CERN or in SAN. They will let you work there, and you might be the person, or you might be the physicist who discovered the new particle, okay, and they might use your name, your surname, as the name of that particle. Okay, where is SAN or CERN? อันนี้นอกเรื่องแต่ว่าเล่าให้ฟังนะครับว่ามันเป็นยังไงครับ Here, okay, SAN or CERN is in SAN or CERN is in Switzerland, but it's very close to the border between here is France, here is Switzerland, and here is the line of the border between those two countries. And SAN or CERN locate in this area, okay, very close to the border, which is this figure. This one, okay, this one located here, and yes, and the particle accelerator would be somehow this. Okay, yes, if you work there, okay, here, you will need to have so many steps in order to accelerate the particle. Okay, and they build up the particle accelerator under the ground. Okay, it's not the same as no, it's not a figure of it's not a figure of particle accelerator actually. Here, okay, they have their own factory, and yeah, here is the tunnel or the pipe. Okay, the particle will be accelerated through this tunnel. Okay, and you could see that the particle accelerator tunnel is built up underground. It's like the train which lies under the ground. Okay, but it's not the route for a train. It is the route for particle accelerator. What is the reason why they build up the particle accelerator under the ground? Because if you build up on the ground, it might be difficult to control, and someone may disturb them, right? And you need a lot of space and so on. And yeah, if you build up under the ground, you don't have to worry that your tunnel will disturb anybody. Okay, and that's the reason. For the particle accelerator in the United States, I think it's in the California. Okay, particle accelerator in the United States. Yeah, they build up above the ground. Okay, for example, you could see here. Yeah, it's like they build up in a circular like way, right here. They let the particle be accelerated in this way. Okay, once the particle is accelerated, they would have high kinetic energy, right? And when it hit the nucleus, you could see some new particles, okay, like this. They build up on Earth. It's not like sand in the Switzerland and France. They build up the tunnel, the particle acceleration inside the tunnel under the ground. And what else? Here is inside the particle accelerator. Okay, you use electromagnetic to accelerate the particle. And what else? There's nothing more, right? Yeah, in sand. Okay, they build up under the ground. Okay, if you want to discover new particle, you have to do the PhD in physics and apply for the job in CERN or CERN. All right, and you have to live in Switzerland or in France. Okay, and in your life, you could explore, you could discover. Okay, you could discover new, bigger particles apart from top quark, bottom quark, tau, lepton, or the neutrino. Okay, there are still many open questions in physics, actually. Okay, let's talk about our story. Electron okay, has the mass of -1, -1. The tau is bigger version of electron of muon, and tau will decay to muon and muon will decay to electron because they are not stable. But the people could discover all these two things because they used the particle accelerator like this. Okay, you accelerate some particles to hit something. Okay, it's like in several kilometers. Okay, 10 kilometers, something like that. Okay, when you will get really high kinetic energy of the particles, and once that particle hit the nucleus of something, you will finally receive new effects. Okay, but you need anyway the particle accelerator. Okay, that's the I don't know, the leading unit on Earth. Okay, I don't know whether there is particle accelerator in Thailand or in Australia. Okay, the antiparticle of electron is the positron here. Okay, usually E minus or E negative, and here is E plus. You could see the same mass of electron for positron. The charge is no longer -1, it's rather +1. The spin number is the same, 1/2. Okay, and the antiparticle for the muon is known as it's called anti-muon. The mass is the same as muon. The charge is +1, is +1 rather than -1. The tau lepton has also the antiparticle, which is known as anti-tau, with the same mass 1.7768 gigaelectron volts นะครับผมก็อายุแก่เกินแล้วนะครับไม่ได้เรียนฟิสิกส์มาไม่มีโอกาสค้นพบพาร์ติเคิลอนุภาคใหม่แล้วนะครับต้องเป็นรุ่นคุณแล้วนะครับเขียนว่าanti-tau, right? These leptons has the negative charge, right, or even the positive charge with the antiparticle version. For the corresponding lepton that has no charge at all, and those are called neutrino. Electron has its own neutrino, which is electron neutrino denoted by nu with subscript e. The charge is 0 and spin number is the same as electron 1/2, the same as quark 2. The mass is very small. Right now we don't know exact value for electron neutrino mass. Okay, the mass of electron neutrino is still an open question. What is that? But it's very hard to determine the mass of electron neutrino because electron neutrino will never act or interact to any other stuff because they have no charge. Okay, unlike alpha particle or proton or something like that, they have charge, so we can detect them easily. But electron neutrino is neutral; it has no charge, so we could not measure the mass of this thing easily. Okay, the bigger version of electron neutrino is muon neutrino, which correspond to muon. Okay, the tau has also its own neutrino, which is known as tau neutrino, and all these three neutrino has its own antiparticles, which are called electron antineutrino, denoted by bar above the letter nu. Okay, and muon neutrino has also its own antiparticle, which is known as muon antineutrino. Tau neutrino has also its own antiparticle, which is called tau antineutrino with the same mass. And please note that the value of the charge here is 0, right? Because neutrino has no charge. So there is no difference at all between antiparticle or the original particle because it has no charge. So what is the classification of the neutrino then? The same spin number you can see here 1/2, 1/2, right? The charge is 0. Unlike electron or muon and tau, they have -1 charge. An antiparticle has 1 charge, but neutrino has 0 charge, and the antiparticles have also 0 charge. So what is the difference? The mass are the same here, okay, for all these 3 particles. I would say the difference for these 2 groups, the neutrino and antineutrinos, is that the lepton number, okay, the typical lepton would have lepton number as number 1, but the antiparticle will have lepton number as -1. Okay, it's not charged. Okay, we will see something about lepton number later, and now we move to boson. Boson is the particle that interact to carry electromagnetic force, or even the strong force or the weak force. Okay, and they have spin number as 1 or 0. Okay, the bosons that have spin number as 1 is called vector boson, and if the spin number of the boson is 0, we call scalar boson, okay, which is Higgs here. Okay, Higgs boson. You know why we call this one as Higgs? Because Professor Higgs, Higgs is the surname by him. Okay, is his surname. Professor Higgs has predicted this one, and he predicted since he was quite young until now. He is 70 years old or something like that. He didn't, as I know, he didn't pass away yesterday, Professor Higgs. And you know, Higgs boson has been confirmed I think in 5 years ago or 10 years ago. And the place that discovered Higgs boson, do you expect, could you guess where the Higgs boson has been confirmed? คุณคิดว่า Higgs boson ค้นพบที่ไหน ก็คือมันถูกคาดการณ์ว่ามันจะต้องมีparticle แบบนี้นะครับแล้วคนนั้นก็ชื่อ Higgs นะครับแต่ก็ยังไม่มีใครทำการทดลองยืนยันได้ว่า Higgs เนี่ยมันมีจริงๆหรือว่าไอ้โบซอนตัวเนี้ยมีจริงเมื่อ10 ปีหรือ 5 ปีที่แล้วเนี่ยนะครับค้นพบแล้วนะครับสถานที่นั้นก็คือที่แสนนั่นแหละครับโอเคไหมถ้าคุณอยากค้นพบอะไรใหม่ๆนะครับไปเรียนเลยนะครับโอเคไหมไปทำงานอยู่ที่แซนครับโอเคyes here is gluon. Gluon is expected to exist, is not confirmed yet. It will interact in the strong force. Photon is already confirmed to exist. Okay, we could find photon, and is the interacting particle in electromagnetic force. Z0 boson has no charge at all. W plus boson has 1 plus charge, as same as electron, and W minus boson will have -1 charge. Okay, they're the same as electron, but the spin number here is different. Is number 1, and the mass is quite big. Okay, the mass is on the order. The mass of boson here, Z0 boson, W plus boson, W minus boson, are on the order of giga electron volt per c². The mass of photon is 0. It has no mass. Gluon also has no mass, and the Higgs boson is even heavier. Is 124.97 giga electron volts. Okay, and that's the whole thing about standard elementary particles. If you want to see the size of something, this is what we have considered in the previous chapter. That's the atomic model, right? There are many orbits for electron, and the size of electron is 10 raised to negative 18. Okay, and atom is on the order of 10 to negative 10, which is 1 angstrom, right? Or you can say also in nanometer it is 0.1 nanometer. And inside the atom we have the so-called nucleus, but this one is written in German. It's pronounced as can, right? It's known as can. This is the nucleus. It's full of nucleon with a proton and neutron. And inside the proton or inside the nucleus, whether it's proton or neutron, we have some particle inside. Okay, the size of the nucleus is around 10 to negative 14, 0.1. No. 10 femtometer, okay, to 6 femtometer. And the size of the proton is 1 femtometer, and the size of the quark will be the same as electron, which is 10 to negative 18, 1 by 1000 femtometer. Okay, the property of the quarks and the property of the quarks could be summarized as this table. Up quark, down quark, strength quark, sharp quark, bottom quark, top quark, right? They have sharp, which is divided by the sharp of electron as 2/3, negative 1/3, negative 1/3, 2/3, negative 1/3, and 2/3, right? The spin number of all quarks is 1/2. And the baryon number, this might not be well known to you. We will talk about baryon number later. Is 1/3, 1/3, 1/3 for everything. The straightness is negative 1 for the straight particle. The sharpness for sharp quark is +1. For the less are 0. Okay, the less have 0 sharp number. The less has 0 straightness. Regarding the bottomness, only the bottom quark has +1 value. The rest have 0 bottomness. Regarding the topness, only the top quark has +1. The rest has 0 topness. Okay, and we arrive at this time and you could take a break, right? So see you on next Wednesday, right? Okay, see you next week. Homework I will assign to you later, the calculation of the released energy in nuclear fusion. Okay, if you have any questions, just let me know. If not, then we're gonna quit the lecture right now. See you on next Wednesday. Bye bye ครับ สวัสดีครับ ขึ้นอันเดียว